So let's talk about how we're going to assess the utility of our model. In other words, we want to make an inference about our slope, beta 1, in our regression model. So we're asking, how useful is this model beta 0 plus beta 1x plus epsilon in predicting y values? Now notice here, if x contributes no information here in predicting y, then our slope is just going to equal 0. In other words, y doesn't change with x. So if our slope is equal to 0, this just drops out and our y value is beta 0 with a random error. So what we're really interested in testing here is the following hypothesis. H0, our null hypothesis, is that beta 1 equals 0. So that means that x contributes no information in predicting y. That's what we're assuming. And then if the sample indicates otherwise, we'll establish our alternative hypothesis, which is beta 1 not equal to 0. So to do this, we're going to need a test statistic here that's based on the sampling distribution of beta 1 hat, the sample statistic for the population parameter beta 1. So that sampling distribution of beta 1 hat, we're going to keep our assumptions about epsilon from the last section. And if we keep those, then the sampling distribution of beta 1 hat, our test statistic should be normal, so it should be bell-shaped distribution. The mean of that sampling distribution should be beta 1. So in other words, that's saying mu sub beta 1 hat, the mean of the sampling distribution for the sample statistic beta 1 hat, is actually beta 1. And then our standard deviation, sigma sub beta 1 hat, is going to be our standard deviation sigma for the data divide by the square root of the sum of squares of xx. Now we don't know the population standard deviation, so we'll estimate that with the sample standard deviation for our data. That will give us S sub beta 1 hat, which is our estimate of sigma beta 1 hat. And that's going to be the estimated standard error of the least square slope beta 1 hat. So here is our sampling distribution for beta 1 hat. Its mean is beta 1. And then it stretches 3 standard deviations to the right and 3 to the left. So this distance in here, that is our sigma beta 1 hat, which we'll estimate with S beta 1 hat. So the standard deviation of the sampling distribution. So with those assumptions, here's how we're going to carry out that test. So our test requirements are going to be the 4 conditions from section 11.3. For a one-tailed test, our null hypothesis is beta 1 equals 0, and our alternative is going to be either beta 1 less than 0 or beta 1 greater than 0, depending on what we hypothesize from the sample data. A two-tailed test is going to be beta 1 equals 0 versus not equal 0. And then our test statistic T is going to be beta 1 hat, so our sample statistic, minus 0, which is the mean of the sampling distribution, and then divide by sigma beta 1 hat, the standard deviation of the sampling distribution. So subtracting off 0 just leaves beta 1 hat, and then in the denominator, we're using our estimate for sigma beta 1 hat right here. So that is our test statistic. And then our rejection regions, we're using a t-distribution here. So notice here, t-distribution, since sigma is unknown. So if t is less than minus t sub alpha, so that's that critical value, depending on alpha, the significance level for the test, or if t is greater than positive t alpha, if you're looking at an upper tail test, and then t less than minus t alpha over 2, or t greater than positive t alpha over 2 if you have a two-tailed test. And then our degrees of freedom for both of those are going to be n minus 2.